Hello, I'm Roman, and welcome back to the series of the videos Neural Networks from Scratch in Go, where we using this book called Neural Networks from Scratch in Python, but we're writing everything with the Golang. And in the previous video, I finished with, first version of the regression model. We started the training, and turns out that the results are not that good. Let's take a look at my implementation, and you can see that the accuracy is very, very, very low, less than 1%, which is not really good. Train did not work out here very well, and with the accuracy, what we do, we measure, first we calculate, what is it? I just want to remind. So what we do, we calculate the standard deviation from all of the predictions, and then we divide it by some magic number. Here it's 250, but it could be changed. There is no straight guidance how to do this. And then we just check how many times we have the we check how many times our model predicts correctly. We cannot compare floating point values just as it is. We need some precision for comparison. So this is why we take in the absolute value from the difference. And we check if it less the precision, then we count it as successful prediction. So we can see that the accuracy is very, very low. So we need to do something with this. And also, yes, I plot the data, and as you can see, okay, so this curved line is our data set, and this weird line is our test, is our predictions. Doesn't look good, right? Animation of the training process. Let's take a look. So basically, it's not moving. Learning rate is the same. Loss is the same, but I think the interesting part is the beginning. So it kind of, how I can do this? Yeah. And then stops. So it's not moving. Recall the rectified linear activation function and how its nonlinear behavior allow us to map nonlinear function, but we also needed 2 or more hidden layers. In this case, we have only one hidden layer followed by the output layer. As we should know by now, this is simply not enough. So, okay, so basically we need to have more and more layers. If we just add one more layer, so this is the first one, that's second, and this is the output. Loss, that's the rest stays the same. So the only thing we take into, yeah, I think I need to start building some sort of the model class that takes array of things, because type it every time is a little bit annoying. And it looks like the accuracy should improve. Okay, our model accuracy is not very good, and loss seems stuck at pretty high level of this for this model. Let's do this. We still don't have it. Okay. What's the second? 64 by 64, probably. Yes. What I'm going to do first, okay, I need to do some refactoring. So the dense 2 will be dense 3, right? Then activation, second activation will become the third one, right? Right. Then I need to create this another set. So this second here it will be 64 by 64 and we'll have the second one. Then what we should do, we do this. This one takes activation 1 output, right? Then it takes dense 2 output, and here it takes from the second one. Okay, then we need this because right now we have 3. So we're still using, okay, and we need to change backward. So loss, thirds, should be here, right? So the second, wait, second takes from the third one, second takes from the second one, and this. Okay, and of course, update params. Okay, let me double check. 1, 2, 3. Okay. First input layer goes into the first activation, and second layer takes from the first activation, second activation takes from the second layer, third layer takes from the second activation, third activation takes from the third layer. Data loss calculates from the last activation, which is the linear one. Regression loss contains all the 3 layers, and accuracy calculates on top of the third activation. So then we need to check the backward method. Loss from third, activation 3 from the loss, then 3 from the 3. Okay, second activation from the third layer, then 2 from activation 2, activation 1 from dense 2. And I need this. Need to change the actual inference, and that will be activation, but not the inputs, that will be the output. Then second, let's say that is the first layer from testing data, the second layer from the thing. There's interesting drop in the accuracy from time to time. Our model accuracy is not very good, and seems loss is stuck at a pretty high level. Really? Okay. As we have already learned, to try to help the model with being stuck at a local minimum, we might use a higher learning rate and add a learning rate decay. In the previous model, we have used the default learning rate. Let's increase it and add a decay. So it means I need optimizer, right? Optimizer learning rate should be this one. I think, I can have a function that sets learning rate, so I can update both values. And then optimizer decay, what was the value? 3. Um, func set learning rate value. What? Oh. Mm. Set. And then I can do that should be the case, right? Okay, I think I will have some errors. Yeah. Mm, I'm using it. Okay. Um, okay, let's don't deal with this for now. Mm. So we have decay, then we can try to run it. But doesn't help the loss. And the accuracy, actually. Mm. Our model still seems to be stuck with even lower accuracy this time. Let's try to use even a bigger learning rate. So we'll have bigger jumps. This one, maybe. Mm. I don't see it's getting better. It's getting even worse. Accuracy drops significantly, and we can observe the lower part of the sine being of the word's shape as well. This one. It seems like we're not able to make our model, to make this model learn the data, but after multiple tests and turning hyperparameters, we could find the learning rate. So basically, I had to just randomly select hyperparameters and see if it's getting approved. So there is no way to Well, it's not the case for me. Still. Mm, okay, probably this value works for their weights, but it's not working in my case. And how I'm supposed to just tweak it and see if it goes better. I can see that the loss is still somewhere in the same place. Mm, mm. It kind of stops on the same loss value for me and the accuracy, and it's not getting further. So what I can do? What can I do here? I mean, just sitting and trying to randomly find. I don't like this. Okay. Debugging such a problem is usually a pretty hard task and out of the scope of this book. The accuracy and loss suggest that updates to the parameters are not big enough, but the rise in learning rate makes things only worse. And there is just this single spot that we were able to find that lets our model learn. You might recall that back in chapter 3 we were discussing parameter initialization method and why it's important to initialize them wisely. It turns out that in the current case we can help the model learn by changing the factor of 0.01 to 0.1 in a dense layer's weight initialization. Um, this one, let's try. Um, oops. Uh, mm, mm, yeah, jumping accuracy is still weird, but more or less, okay, this is a very high accuracy. Okay. But then you might ask, since the learning rate is being used to decide how much of the gradient to apply to the parameters, why does changing these initial values helps instead? As you might recall, the backpropagated gradient is calculated using weights, and the learning rate does not affect it. That's why it is important to use right weight initialization, and so far we have been using the same values for each model. If we, for example, take a look at the source code of Keras and neural network framework, we can learn that it draws samples from a uniform distribution within limits, where a limit is the square root from 6 divided by fun in plus fun out, where fun in is the number of the input units of the weight tensor, and the fun out is the number of the units in the weight tensor. Python integer used to seed the random number generator. Blah, blah, blah. This code is part of the Keras2 library. The important part of the both is actually the comment section, which describe how it initialized weights. We can find these are important pieces of the information to remember. The fraction that multiplies the draw from the uniform distribution depends on the number of the inputs and the number of the neurons and is not contained, it's not constant like in our case. This method of installation is called Glorat uniform. We, the author of these books, actually have had a very similar problem in one of our projects, and changing the way weights were initialized changed the model from not learning at all to a learning state. For the purpose of this model, let's change the factor of multiplying the draw from the normal distribution in the weights installation of the dense layer to 0.1 and rerun all of for the above attempts to compare the results. So it will actually work with the standard atom without changing in the learning rate. That's what you want to tell me? I think the last one I tried was kind of overfitting. Yeah, I think this is... I'm curious why I have jumps. The loss value is very small. Accuracy 97%. The model was previously stuck and has now achieved high accuracy. There are some visible implications like the bottom side of the sign, but maybe I should draw it once again. X equals to make plot 64 1, x0 equals to x test expected a selector. Size, okay. 1. Can't use make. X0 equals to x test. What is happening? Oh, okay. X test. Then I have y 0 equals to activation 3 output and then scatter x. Okay, let's... So this is the predictions. So that's what our model. Interesting part is this one, kind of. The top one is much smoother. The down one is a little bit sharp. The model was previously stuck on the hierarchy. There are some visible imperfections like at the bottom of the sign, but the overall results are better. So then we'll try with the learning rate and decay. It looks like it works much smoother. Okay. Learning rate, I think 0.01, right? Current 0, 1, and decay 1 e minus 3, right? Yes. So that should have even bigger accuracy, but it feels like I'm no 10k. In my case, it's not just growing, but it's actually jumping, which is, I mean, still don't understand. It's kind of weird. And the loss, no, loss seems fine. But in the end, the model is okay. I wouldn't say it's smoother. Okay, then I will check another previous stack was trained very well, achieving very good accuracy. But yeah, I mean, in general, that's the very good accuracy. Well, okay, so they have these jumps in accuracy too. This is the interesting part for me. The jump in accuracy in this case of the set of the optimizer settings shows the learning rate is way too big. Oh. But even then, the model learned the shape of the sine function considerably well. So the default learning rate was too high. So maybe we should change to something like this with decay. Kind of, I mean, it still jumps. Okay, maybe even smaller. Or like something like this. Does it make sense? Okay, that's too small. It's not learning. Um, okay. This one. Okay. But this is, I mean, I think I can play with this more. For example, use 2 or 3 in the end, and it should, or maybe use a smaller decay. So well, maybe yeah, starting learning rate is the same, but smaller decay, or bigger decay, so it will change a little bit faster. But anyway, model trained to best fit the sign data after replacing. The hyperparameters yields the best result again, but not much. As we can see at this time, our model learned in all cases with using different learning rates, but did not get stuck if any of them. That's how much change in the weights and initialization can impact training the process. Interesting, what if I will run the previous model with this one? Okay, this is the whole code at this point, but I have a feeling that we're done with the regression. Model object. Just when I thought that we need to write some code to easier write these models. Well, actually, we're going, I think, into a very interesting part because this is the way where I can go full, how it's called, full crazy, something like this. So we probably will create the model class that will be easier to use, because right now it takes a lot of the time to do all of the things. Then there is an interesting part about the real data set. So we'll actually try, I know this NIST data set, and this is actually cool that we can try to use what we implemented, model evaluation, saving and loading the models and the parameters, and then actually the prediction and inference. And I think in the end, I will try to, create some sort of the, web service that will use what I wrote, and we can, we can launch the instance of the web server, we can call and get the predictions. Let me check the recording time, 36 minutes. It's not that much. I think I can continue. Then let's go next. Build a model that can perform the forward path, backward paths, and accelerate tasks like measuring their accuracy. We have built all this by writing a fair bit of code and making modifications in some decently sized block of the code. It's beginning to make more sense to make our model an object itself, especially since we will want to do things like save and load this object to use for future prediction tasks. We will also use this object to cut down on some of the more common lines of code, making it easier to work with our current code base and build new models. To do this model object conversion, we will use the last model we're working on, the regression model with data. There we have it. Once we have the data, our first step for the model class is to add in the various layers as we want. Those we can begin our model class by doing so for layers. This allows us to use add method of the model object to add layers. This alone will help with legibility considerably. Let's add some layers. Okay. Besides adding layers, we also want to set a loss function and optimizer for our model. To do this, we'll create a method called set. The use of asterisks in the parameter definition knows that the subsequent parameter loss and optimizer in that case are keyword arguments. Since they have no default value assigned, they are required keyword arguments, which means that they have to be passed by names and values. And now we can add a call to this method into our newly created model object and pass the loss and optimizer object. So XY model, then we add the parameters, then we set loss and optimizer. After we have set our model layers, loss function optimizer, the next test is to train. We'll have the train. Okay. We then can add the call to train method in the model definition. We'll pass the training data, the number of the epochs. Okay. To actually train, we need to perform a forward path. Performing this forward path in the object is slightly more complicated because we want to do this in a loop. And we need to know the previous layer's output to pass data properly. One issue with querying the previous layer is that the first layer doesn't have a previous layer. First layer that we're defining is the first hidden layer. One option we have then is to create an input layer. This consider layer to the neural network doesn't have any weights and biases associated with. The input layer only contains the training data and will only use it as the previous layer. Okay. So far what I think, okay, the forward method set training itself of the properties common with the other layers. There is no need for the backward methods here since we'll create it. The next thing we're going to do is to set previous and the next layer properties for each model's layers. We'll create a method called finalize in the model. Layer inputs, count. The code creates an input layer and sets next and the pref reference for each layer contained within the self layers. So we can, well, it's basically it is a, how it's called, two sides linked list. So we can go in one direction into another direction. The code creates an input layer and sets next and previous. I'm going through this quickly just to get an understanding of what they want to do. But since I'm writing this in the Go, which is very strong with the types, I will need to do some of the refactorings to make this work. And I think I will need to write a lot of the things. For example, especially with the data, so far I had X as the data, as a math prediction, as math dense, at the dense class, but for the target classes, I usually had a slice of integers, and only in the, where it was, only in the regression model, I had a slice of the float values. And in order, for example, to be like, if I want to be able to create a model with any puzzle, also the layer and activation, they have forward and backward method. The problem is, I think, with how it's called, with the function declaration, because if we take a look at, I know, for example, loss, it takes, no, okay, loss, I think defined, loss is not a good example. What was in the end? Activation. Well, okay, maybe with the activation it's not that hard, because activation and the backward takes one input, relu takes one input, sigmoid takes one, softmax takes one. Okay, then it can be covered uh, with an interface. With the layer, we have the dense layer with forwards and backward. Okay, basically the same. We have the dropout, same. Okay, so I can cover activation and the layer with an interface. And in my case, the model add method will take an implementation of the interface. Why it's needed? Because layer will be implementing this interface as same as the activation. With the loss and the optimizer, they will have different protocols as well. But if we take a look at all of the, well, apart from the calculations, yeah, I need to think change it. For example, binary cross entropy, they have calculate forward backward. Same here and same here. Okay, so I can cover the loss with another protocol, and then I have the optimizers, which pre-update, update params, yeah, the same. So I will need to create, I think, three protocols at least for this part, and for this part. Then there is a thing about the data, which means that I will need to change what I'm passing. Then there is a thing with the, I think, the binary. With the binary and mean square error and mean absolute error and mean square error, I will need to change them in the way it was implemented with the average, because right now this is built in a way, yeah, like a road. Prediction has only one value for the sample. But basically that should be array of arrays or just another dense. And then I can go with through the rows and the columns. So maybe that will be actually my first thing I need to change. Can I? Okay, I think I will do this. So I have to do first refactor loss functions to take dense instead of float instead of int 8 and float 64. Fix um, mean absolute error, mean square error, and I think it was with a binary cross binary cross entropy to work with array of arrays for target data. I think this is the right. Then create interface for layer process activation. Then for loss functions and create interface for optimizers. Content. First line in the file should be a top level heading. Okay. To-do list. That's better. Okay. All right. I think I will stop for today. Also, timing is about right. And I will check how the result should look like in the Python. I mean, I will take a look at all of the things later and see how it should work. There are some interesting things. And I guess this chapter is all about the creation of the model class and using it. Make the full train method. Okay. Move finalize, blah, blah. There are a lot of the code. I think this is full code. Okay, so I will definitely need to check this before I will go with the Go, just to find all of the all possible things that I can miss. Not this one. And yeah, and I think for the next couple of videos, I will do mostly the refactoring and checking that everything is okay. And once we've done with this, we will go to use the real dataset. Thank you for watching, and I see you tomorrow. Bye-bye.